In this video, we're going to be starting our talk about simple gas laws. We are going to begin by talking about the relationship between pressure and temperature. We defined earlier that pressure had to do with the frequency of collisions and the impulse of collisions against the sidewall of the container. And temperature had to do with the average kinetic energy. That's not how you spell kinetic. So if we increase the temperature, then our gas molecules are going to be moving faster. If they're moving faster, they're going to hit the sidewall of the container more often and harder because now they're moving faster. It's the difference between me tossing a basketball at you and me shooting a basketball out of you through a cannon. The cannon is going to hurt a lot worse because it's moving a lot faster. So we are increasing the pressure as we increase the temperature. So as we increase temperature, we are doing two things that will increase the pressure on the sidewall of our container. So since these two arrows move in the same direction, these two terms are known as being directly proportional. If we increase one, we increase the other. If we lower one, we lower the other. They're going to be moving in the same direction. We can actually take measurements at different temperatures and pressure and plot them on a graph, and you can see that they form a very, very straight line. You might remember from a math class that the general equation for a line is y equals mx plus b, where b is the y-intercept. In this case, our y-intercept is 0. So if b is 0, then that term doesn't even need to be there. And so y here is pressure, m is a constant called k, which is the slope of the line, and then t here is the temperature. So we end up with an equation of the line, P is equal to KT. This is known as Gay-Lussac's law, better known as Amonton's law. This is the more proper name, but it's always referred to as Gay-Lussac's law. He was misattributed with the law of discovery. But whatever, historical accident. So if we take our P equals KT equation, rearrange it to solve for K, we can take one pressure and temperature point and use this to solve for a second pressure temperature point. So we can take, these are both equal to K, and so we can make these two terms equal to one another. So we can say P1 over T1 is equal to P2 over T2. And so this is just at time 1. The first point in time, second point, I don't care. First point, second point, initial, final, final, initial, whatever. So you can say like initial and final. Here's an example problem applying Gay-Lussac's law. It reads a sealed 2.5 liter container of gas containing 1.5 moles of gas is initially at 0.500 atmospheres at 25 degrees Celsius. What will be the pressure at 125 degrees Celsius? So we can look at the units here. Liters is volume. But also it says our container is rigid, and so that means this is constant. It does tell us how much gas is in our container. Moles of gas is equal to N, but it doesn't mention anything about the moles of gas changing. It does say here that it's sealed, so our container is sealed, that means no gas can escape, so N is constant. When we say things are constant, that means they are not changing. We need to look at things that are changing. So our initial temperature, or our initial pressure, atmospheres is a pressure unit. So our initial pressure is 0.5 atmospheres. Our initial temperature T1 is 25 degrees Celsius. What will be the pressure at 125? So we do not know our second pressure. That's our unknown. And we are given our final temperature. Earlier, I said that we have to convert our temperatures into Kelvin. We have to do that first because this is an addition conversion, and so it's not the same if we don't do it beforehand. So let's go ahead and convert both of those into Kelvin. So I opened up my calculator app so that you can see the conversion being typed in. So now we have both of our temperatures in Kelvin. That's exactly what we want. Now we can set up our equation. We know the relationship is P1 over T1 is equal to P2 over T2. I'm trying to solve for P2, so to isolate P2, I'm going to multiply by T2 on both sides. So we're going to have P2 is equal to P1 over T1 times T2. So that's going to be equal to 0.500 atmospheres. T2 is 398. And then T1 is 298. So if I type that into my calculator, so I have 0.5 times 398.15 divided by 298.15. And so that is equal to 0.6677. I'm going to need just two significant figures. Nope. Yep. Nope. Three significant figures. This was not involved in the calculation, and neither was this. And then temperatures were both significant to the ones place, which is 3 sig figs by the time they were used in math. So that's going to be equal to 0.668 atmospheres. We also need to do a sanity check here. Since we know that our temperature is increasing, our pressure should also be increasing. That means that P2 should be more than P1. And so 0.668 is indeed more than our initial pressure. And so now we know that we did plug in our temperatures and stuff into the correct locations. It's always good to do that kind of conceptual check, because if this was like a multiple choice question, you could eliminate some answer choices that were lower than the initial pressure. Here's a practice problem for you. It reads, a gas is collected into a rigid 4.50 liter container at 22 degrees Celsius and 745 millimeters of mercury and sealed. The container is cooled until the pressure inside is 557 millimeters mercury. What is the final temperature in degrees Celsius? Go ahead and pause the video and work this out. Unpause the video when you're ready to check your math. Okay, let's go over this. So we will not need to know our volume of the container because it is rigid. It's not changing its volume. So that's extra information we did not need. If we analyze this, we are saying it's cooled and the pressure inside is dropping. So our pressure is going down. Our temperature should be going down. That means that we expect our final temperature should be less than 22 degrees Celsius, which is the initial temperature. So if we outline our different variables, we have our P1, millimeters of mercury as a pressure unit, so that's going to be our initial pressure. our temperature is 22.0 degrees Celsius. And we're going to have to convert that into Kelvin. We always have to convert that into Kelvin. On OLI, they'll just expect to use 273. I'm going to be using 273.15, more precise. And then our pressure is 557.0 millimeters of mercury. And we're asked to solve for T2. So our equation, P1 over T1 is equal to P2 over T2. We can solve for T2. T2 is in the denominator, and so that means I'm going to have to multiply both sides by T2 in order to cancel it out. Now it's in the numerator, so it is something I could actually solve for. Now I have to isolate it by getting rid of this term. I'm going to get rid of that term by multiplying both sides by T1 and dividing by P1. Now that term cancels out. So I've done my algebra, and I'm left with the equation T2 is equal to P2 over T1 over P1. So I can plug in my numbers. It doesn't matter what pressure unit I use, so I can use whatever pressure unit is given to me. But I do need to make sure that my temperatures are in Kelvin. So 22 plus 273.15 is equal to 95.15 Kelvin. And then I am solving for P1, which is where I have to plug in my P1. Okay. So now I know that my T2 is equal to 575 times 295.15 divided by 745.0. And so T2 is equal to 27.80 in Kelvin. The millimeters of mercury cancels out, and I'm left with Kelvin. So that's in Kelvin. I'm asked for degrees Celsius. So then I have to convert this back into Kelvin. By subtracting 273.15. And so that means that I have cooled my gas to be negative 45.35 degrees Celsius. How many sig figs do I need? Let's figure that out. This is significant to the ones place here, and so that's going to give that 4 digits. That's going to have 4 digits. I need 4 digits. So there we go. I do not need 4 digits. That's ignoring the subtraction rule for sig figs. This is the 4th digit that's significant. That means my answer is significant to the 10th place only. So negative 45.3. Also good to double check that your final calculated temperature is lower than your initial temperature, just like it should have been.